Hi again. So far we have covered most of what we need to know about the Laplace transform. Namely, we have defined the Laplace transform, we have derived Laplace transforms for various very common functions such as 1, the Heaviside function, exponential, t to the nu, sine and cosine functions. Moreover, we have stated a few properties of the Laplace transform. First of all, it is linear. The Laplace of f plus g is the Laplace of f plus the Laplace of g, so long as these exist, of course. And the Laplace of constant times a function, we can move the constant outside. Then we gave this property for delayed functions. So if a function starts at a time t0 and it is 0 before that, this is how we can compute the Laplace transform. And we use this property, number 7 here, to derive the Laplace transform of functions which are defined piecewise. Then in the last lecture we gave the most important property, which is this one, which allows us to compute the Laplace transform of derivatives. And we see that the Laplace makes the derivative disappear. It turns the derivative into multiplying the Laplace transform by s. So L of f prime is s times f uppercase of s, minus a constant term over here. And this property is very important because it allows us to turn a linear ordinary differential equation into an algebraic equation. So today we will do one more property, because we have given all these, we are able to compute Laplace transforms for most signals, but there is a class of very important signals, especially in electrical engineering, that we haven't quite covered yet. And these are periodic signals, such as, for example, square waves. So how do we derive the Laplace transform of such a time domain function, or even rectified sine waves? This is given by absolute value of sine of t, or absolute value of sine of omega t. So how can we find the Laplace transform of such periodic functions? But first of all, what is a periodic function? A periodic function is a function which follows a pattern in time, which repeats itself. For example, the function sine of t starts at time t equals 0. Let me say again, all functions in the time domain that we study are defined over the non-negative timeline. And this function goes from 0 to 2 times pi. And then after that, if we just copy this function from 0 to times pi, if we copy it here, then we will have the function from 2 times pi to 4 times pi, and so on. So we can define the function only from here to here. And this number here, this time, is called the period of the function. Let us write the proper definition of a periodic function. So it is called periodic with a period p if the value of the function after every t uppercase is equal to the value of the function at time t. So here, for example, take any time t, take this time t, take the value of the function at that time t, and move to the right by t uppercase. And at that point, you will find exactly the value of the function again at time t plus t. The function will have exactly the same value as what it had before t uppercase. And then again the same here. If you take here to be some other time t prime, and you move to the right, you go to time t prime plus t uppercase, the function will have exactly the same value again. And then there is this beautiful result regarding periodic functions, that allows us to determine their Laplace transform. You don't need to memorize this formula, it is indeed a little lengthy, and we will not give the proof, but you need to know that this theorem exists and what we can do with that, so that you can, if necessary, you can look it up and use it to find the Laplace transform of a periodic function. So for example, we can plug inside here the function f of t equals sine of t. We know that t uppercase in our case is 2 times pi, so t uppercase here will be 2 times pi, and then we will have that the Laplace transform of sine of t minus s, and here 2 times pi, and integral. And if you do the math here, after quite some effort, you will end up with 1 divided by s squared plus 1. Of course, this is not the best way to determine the Laplace transform of sine. We've seen a much better and much easier way to do that. But you can verify that this formula works with this periodic function. But this is not why we gave this theorem. We rather gave this theorem for periodic signals for which it is not entirely clear how we can determine the Laplace transform. Take for example this one, which is 1 from 0 to some time, let's call it t uppercase. Let's not call it t uppercase, let's call it a lowercase. And then it is 0 from a to 2a, and then it is 1, and so on and so forth. So the function is periodic, with period t uppercase is equal to 2 times a. And it suffices to define the function from 0 up to 2 times a. Let's define this function. And we can say it is periodic with period t uppercase equals 2 times a. Then the Laplace transform of this function, of this periodic function, now look at that. It is this term times an integral, but an integral just from 0 up to 2 times a, not up to infinity, just 2 times a. And we know that this function f is 0 between a and 2 times a. So it only makes sense to integrate it from 0 to a, where this function is equal to 1. So we're talking about the integral from 0 to a, e to the minus s tau, and the result now is given by that. The minus sign here we can move outside, and you can even simplify it just a little more. You can write it more compactly in just one fraction of 2 terms. So that's the result. And you see here that instead of using the definition, in which case we would have to go from 0 up to infinity, we can just compute an integral from 0 up to a, and we can derive easily in just one line the Laplace transform of this periodic function. Now, as an exercise, you can do, first of all, you can do something very simple. Find the Laplace transform of this other function, which is 0 from time 0 to time a, and it is 1 from a to 2 times a. There are 2 ways to go about it. One is, of course, it's clearly to apply this theorem because this is a periodic function with period 2 pi. Another way to solve this exercise is to use the previous result of the previous exercise. You must see now that this looks really very similar to the Laplace transform we derived in the previous exercise. So think about it. So this is exercise number 1, exercise number 2. So you have this triangular pulse. It goes from 0 and at time a it goes to 1, down to 0 on time 2a, and so on. Again, this is periodic with period 2a. And the third example, the rectified sine wave. And with this video lecture, we conclude a big chapter on the Laplace transform, and now we can pretty much compute and derive the Laplace transforms of a very large family of functions. And with that, thank you very much for watching, and until next time, goodbye.